Today I'm going to introduce you to a factory for making rings. Okay, and it makes very interesting non-commutative rings. So the rings that this factory produces are called path algebras of quivers. So what is a quiver? Let me begin with an example. So here's an example of a quiver. You have a bunch of nodes, 1, 2, 3, and then you have a bunch of arrows. So the arrows A, B, C. You can even have arrows going in both directions, D. Okay, so formally what is a quiver? Formally a quiver consists of 4 pieces of data, V, which is a vertex set, then E, which is an edge set, then there are 2 functions called the source function S from E to V, so this is called the source function, and then finally T from E to V called the target function. In this example, they are as follows. V is just the set 1, 2, 3. E is the set A, B, C, D. And let me tabulate the source and target functions for A, B, C, and D. So you have A, B, C, D, and we can ask for their source and target. So source of A is 1 because the arrow starts from A, and the target of A is 2 because the arrow ends at A. Source of B is 2, target of B is 2. Source of C is 3, target of C is 2. Source of D is 2 and target of D is 3. Okay. Now, given two vertices, let's say I and J of the quiver, a path, so a path from I to J is a sequence of edges, and I'll write this sequence from right to left, A1, A2, AN, such that the source of A1 is I, the target of A1 is the source of A2, and so on. The target of AN minus 1 is the source of AN, and the target of AN is J. Okay, so in this example, I can write down a path from 1 to 2 as, so I have to start with 1, I have to follow arrows, and each time I follow an arrow, I write down that letter, and I write them from right to left. So for example, I start with 1. Let's use the arrow. The only way to get out of 1 is to use the arrow A. Okay, now I'm at 2. So what do? I could either do B or I could do D. Let's do B. And I'm back at 2. I'll do B again. So I'll write it as BB, but I'll write it as B squared. That's the usual convention. Then I can go to 3 using D. And then I can come back to 2 using C. And then I'll do B again and end up at C. So this is a path from 1 to 2. A special kind of path is the trivial path. So for every I in V, we denote by epsilon I the what is called the trivial path. From I to I. So what we are thinking of this path as doing is you are at the vertex I and you don't use any arrow at all. So this is a path of length 0. Okay, so this path means do nothing starting at I. Okay, and so E star is the set of all paths in Q. Okay, and if P equals an minus 1 dot 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 a1 is in E star, we write S of P, the source of P, to be the source of a1 and the target of P to be the target of an. Okay, so then this P is a path from source of P to target of P, and the empty path corresponding to I is a path from I to I. So this will be the convention. Okay, so so much for the definitions of quivers and paths in quivers. Now we are ready to define the path algebra of the quiver. For this, we need to fix a field F. Any field, your favorite field. You can even take a ring. Okay, and then I define the path algebra of Q, of a quiver Q over F is denoted by F square brackets Q. Okay, so this is going to be a ring and is the F vector space with bases one sub P, where P is a path in Q. So this E star, recall, denotes the set of all paths in Q. So typical element of FQ is of the form summation P in E star AP 1 sub P. Okay, and we can talk about, now we have, I'm going to turn this thing into a ring. So I have to define multiplication. In order to define multiplication, we consider concatenation of paths. So suppose you have two paths, P equals A1, A2 dot 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 AN, and Q equals B1, B2 dot 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 BM. Then if target of AN is the source of B1, then you can define QP to be BM dot 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 B1 AN dot 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 A1, and this is a path. And it is called the concatenation of Q and P. Okay. Now I define multiplication in the algebra FQ by defining the multiplication of two basis elements. So it's defined on basis elements as follows. 1q multiplied by 1p is defined to be 1 sub qp if the target of p is equal to the source of q and 0 otherwise. And using bilinearity, this so you want to say that the multiplication is linear in each of the arguments, so this can be extended to the path algebra. So you define summation AP1P P belong to E star multiplied by summation Q belong to E star. Oops, the star goes up. BP1P is defined as summation P of Q in E star APBQ 1, oops, this is Q 1P 1Q. So this is the definition of multiplication in the path algebra of a quiver. So it's not difficult to check that the path algebra of a quiver is a ring with this definition of multiplication. Addition is just the vector space addition. I won't do the check of that it's a ring. If you want, you can try it yourself. Instead, we look at some examples. So here's the simplest example. Maybe I'll call it example 0, where Q is the quiver, where E is just a singleton set 1, and let's say V is the empty set. So I don't have to specify what S and T are because they're functions from the empty set. So in this case, we will just represent it by a single point, which is 1, and there are no arrows at all. Then what is FQ? So Q is 1 empty set and whatever S and T, the functions from the empty set to the set 1. So FQ then has basis. So what are the paths? There's only one path, which is epsilon 1. So the empty path from 1 to 1. And if you multiply epsilon 1 by itself, you get epsilon 1. This is just isomorphic to the ring C. Oh, whoops, this should be F. This is isomorphic to the field F, which we think of as a ring. Okay, so that's a trivial example. Let's look at a slightly more interesting example. And let's take E to be 1. But now I'll have V to be just one path, which I'll denote by T. And S of T equals T of, whoops, maybe I shouldn't call it T. Let me call it U. S of U equals 1 and T of U equals 1. So if you want to draw this quiver, it looks like this. You have this one node 1, and then you have U is one arrow going from 1 to 1. So then E star consists of all the paths start and end at 1. There's the empty path, then there's U, then there's U squared, there's U cubed, and so on. So F of E star is just the vector space spanned by epsilon 1, U, U squared, U cubed, and so on. And what we have is 1 sub U multiplied by 1 sub U to the power K multiplied by 1 sub U to the L is 1 sub U to the K plus L. So I claim that KE is isomorphic to FE, the polynomial algebra in one variable, and this isomorphism is given by taking 1 sub U to the K to the monomial U to the power K. Okay, this is easy to check. Let's look at one more interesting example. Let's take, I'll just draw the quiver now. So you have two nodes, 1 and 2, and we have one arrow which we call A. So what are the paths of Q? So there are three paths that I can find. There's epsilon 1, there's A, and there's epsilon 2. So epsilon 1 goes from 1 to 1, A goes from 1 to 2, and epsilon 2 goes from 2 to 2. And the products are given by A epsilon 1, that means first you go from 1 to 1 by the empty path, and then you go from 1 to 2. So this is A. Then we have epsilon 1A is 0 because the target of A is 2 but the source of epsilon 1 is 1. Then we have A epsilon 2 is 0 and epsilon 2A is equal to A. So this algebra has 4 basis vectors and this is how they multiply. Now this algebra actually has another familiar avatar. Consider the following algebra: A to be the set of all matrices of the form A, B, 0, D, where A, B and D are arbitrary elements of F. Now if you add or multiply two upper triangular matrices, you still get an upper triangular matrix. So this is a ring. Right? And then you take epsilon 1 goes to the matrix 0, 0, 0, 1. Epsilon 2 goes to the matrix 1, 0, 0, 1, 0, sorry. And A goes to the matrix, yeah, maybe I shouldn't have called this A. Let's call this C, B, 0, D. And A goes to the matrix 0, 1, 0, 0. Now, if you do the matrix multiplication, so if you take the matrix corresponding to A, that is 0, 1, 0, 0. So let's call this map phi. So this this is defined on a basis element. So this gives rise to a map phi from FQ to A. And if you look at this, so this is phi of A, and this is phi of epsilon 1. That's 0, 0, 0, 1. If you multiply them, you will get 0 in the first column. In the second column, you will get 1, 0, which is phi A. So phi of A times phi of epsilon is phi of A epsilon 1. And similarly, you can do all the other checks and you can see that phi is actually defines a ring homomorphism. And in fact, phi is an isomorphism of rings.